All right. Good evening, everyone. I hope I'm audible today. Okay. Let me check my recordings one second. Okay. So, good evening, everyone. Today we are going to talk about thermodynamic functions. We will solve some relations, some equations with thermodynamic relations. Um, uh, your assignments. And if you have any questions regarding the last week sessions or regarding the um, the course materials, you can ask me now. I think we have three people here. I will give you 5 minutes or so. If you have any questions, you can ask me. Audible, everyone?
So, hello.
Yes, Francis, go ahead.
So, what do you mean by this strong function, weak function?
I'm not sure. So, where do you come across this strong function and weak function? So, I'm
Actually, I was doing one problem. In that question, they just asked what is about the strong and weak function.
see. So, I've come across only. Maybe I need to take a look at your questions, Francis. Would it be possible to share it with me?
I will share it, sir.
So, is that is so? Which topic is that related to? Francis, which topic is that related to? Francis, I think you are in mute.
So, can you see the screen?
Yes, yes. So, which question is that?
So, this 10th question, pressure exerted by a gas in a closed container is.
Okay, okay. So, so the weak function and strong function is, if it is a weak function, it talks about dependence, how it is. So let's say for a change, small change in pressure, what is the change in density and temperature? Is it weak or strong? So it is like looking at point of slope, right? So slope is not very high or slope is very high. It depends on that. The pressure exerted by a gas in a
So,
closed container is actually
so is it related to slope?
so you can so it is like what is it? So if let's say if you use a ideal gas and the equation of state will be as so can you stop sharing your screen?
Okay, sir.
So that is the question, right? Is there
Yes, sir.
so it is purely based on mathematics. If you look at it, let's say pressure exerted by the gas in a container is going to be let's say PV is equal to RT, right? So this is what we know. This is from ideal gas equation state. Now, if you look at it, there is a direct dependence. Let's say if there is a small change in pressure, there is a huge there will be a substantial amount of change in density and temperature. This V is nothing but specific volume, so you can rewrite this as rho RT, right? So you see a direct dependence, right? So say if you write a differential, Tp is equal to, how would you write it? P is a function of rho and T, right? P is equal to, so dou P by dou rho at constant T dt plus dou P by dou T at constant rho d rho, right? So let's say if you take this relation and find dou P by dou rho, it's going to be RT. So and dou P by dou T, it is going to be uh, rho times R, right? At constant density. This is at constant temperature. Let's say if you substitute it back, what happens? RT dt plus um, this is going to be rho R d rho, right? So let's say, so this is the change for a small change in pressure. The change in so for a small change in temperature, you are going to have large effect in density and temperature. Right? So let's say if you do an integral, what happens? There will be T dt and rho d rho, right? So there is a huge dependence on this density and temperature, right? So it is mathematically, if you look at it, it's just a function, or you can even simply say it based on this relation. If you see P is equal to rho R and T. So when there is a change in density, there is going to be change in pressure. When there is a change in temperature, there is going to be change in pressure. Uh, there are some functions like, let's say, some other functions. Uh, how can we put it? Like it only depends on, even we can actually ignore such changes. Let's say it is not directly dependent, or it is not dependent in this form, P is equal to rho RT. Instead, let's say it is dependent on some other form such that a very small change in rho doesn't give that good change in pressure. Actually, you can ignore this. So when you have such kind of dependence, then it would be called as weak function. So that is what I think they meant in that question. Um, does that make
Okay,
sense,
so
Francis?
so actually, if we can write the pressure in terms of differential of the, uh, I mean the density and temperature. So maybe we can
Right. So,
call it strong function.
right. So let's say for a, if you write dp by dt, let's say, right, it is going to depend on R and T, right? So it is dependent on temperature. Similarly, dp by d rho, right? Let's say keeping temperature constant, it is going to depend on R and rho, right? So let's say if this is constant, then it is a weak function, right? But here it is not constant. Here it directly depends on temperature, right? So does that make sense? Or maybe
So can
from
you
this relation?
say once again that thing? I mean, you have explained now. First, we make it the RT the constant. Then
Right. So this is clear, right? This part.
the first one is clear.
This part is clear, right? How did we
Yes, sir.
write this? So if you just focus this, let's say for a small change in pressure, right? Keeping temperature constant. If you look at it, you are going to have very the temperature is going to depend on that. So for small change in pressure, or let's say for small change in density, uh, the the change in pressure is going to depend on R and T. So it is a weak function, it's a strong function of temperature. So you see uh, the change in pressure is actually coming out to be T dt and rho d rho. So that is a strong dependence. Let's say if you integrate it, you are going to have a strong dependence. That is what I'm trying to say.
Okay, sir.
Okay. Um, there might be some functions which may not be that much strong dependence. Um, let's say you take pressure for a fluid. Okay. It mostly depends on, let's say, if you consider uh, a fluid also undergoes changes in density sometimes when there is a change in temperature, but that is very minimal. We use it volume expansivity or some beta function, right? So let's say we can write density of a fluid to be something like rho naught plus beta times t, something like that we can write, right? In this case, uh, even when you change temperature over a wide range, let's say 100 to 100 degrees Celsius, or let's say 20 degrees Celsius to 100 degrees Celsius. Let's say if you change that much, the density will be changing only like 2% or 3%. Then it becomes a weak function. Okay. It's just quantifies the dependence. Let's say for fluid it is a weak dependence, for gases it is a strong dependence. That is what they meant about it when they asked that question, I think. Okay. Is that fine,
Okay, sir.
Francis? Okay.
Yes, sir.
All right. Are there any other questions? Is there any other questions
Sir,
related to
I
the
think I
topic?
will ask the
Francis, go ahead.
I will ask the question at the end. Otherwise, the session will be.
Okay, okay. All right. Ha. All right, no problem. Um, you can also ask me at the end. So if there are no more questions, maybe I will go forward with the problems I have today. Today I have almost like I have four problems, which is related to the thermodynamic relations or Maxwell relations, and this is going to be more mathematical today because you may need to get familiarized yourself with partial equations, differentials, total derivatives. So all these four questions are made based on that. So let's get started. So the first question we have here is to consider an ideal gas at 300 Kelvin and 100 kilopascal. As a result of some small disturbance, the condition of gas changes to 305 Kelvin and 96 kilopascal. Estimate the change in specific volume of the gas. Let's say there is some container and there is ideal gas filled in it, right, with this condition, and there is some small disturbance happening to that, and because of that the temperature and pressure is changing. So we were asked to find specific volume of the gas. So how can we find this? We write it down. So it's going to be, so P1 is 100 kilopascals, which is the initial state, and temperature T1 is 300 Kelvin, and T2 is 96 kilopascal. T2 is going to be 305 Kelvin. How do we find this? We need to find V1 and V2. Or the other way, it's so we need to find the change in specific volume, nothing but V2 minus V1. So write it like dV or delta V. So whichever is convenient. And one assumptions they gave is it is an ideal gas. How do we find it? There are actually two ways of finding it. One should be straightforward. Can anyone guess? Okay, everybody is silent today. So we already learned about differentials, right? So we know we need to find specific volume, and what we know about specific volume can be. We also know that for a simple compressible substance, we can use we can write all the properties as a function of two independent variables, right? Here P and T are the variables, so we can write specific volume as a function of P and T, right? We need to find dV, so that is the only uh, question asked, right? Estimate the change in specific volume of gases. So if we need to find dV, uh, we just need to perform this total derivative for the dV. So this is nothing but total derivative is going to be, so since v is a function of both p and t, initially you will keep t as a constant and differentiate with respect to p. So it's going to be a partial derivative, right? Dou v by dou p at constant t and dp plus dou v by dou t at constant p dt, right? So this is how we write this. The total derivative. This is how we take total derivative of any property, because that is going to depend on only two independent properties. Okay. Now we calculate dou v by dou p and dou v by dou t. So we know it's an ideal gas. So we can write PV is equal to RT, right? This is the ideal gas equation of state. So let's say if we write V is equal to RT by P, should be straightforward to find dou V by dou P, right? So dou V by dou P at constant temperature T is going to be just R by P, right? And similarly dou V by dou T at constant P is going to be, did I repeat it? Sorry, this is R by P, right? This is where, okay. Now dou V by dou P at constant T. How do we write it? So it's going to be uh, 1 by P. So how do we write it? Dou V dV. One second.
So actually, do we need to go for this differential form? I can like why can't we use that PV equal to MRT equation? And
Yeah, why can't we use that? So that's what I told in the first, right? There are two ways to solve it. This is just for you to familiarize with the total derivative.
Okay, sir.
Okay,
Okay, sir.
so the yeah, you are right. You can just go forward with we can find V1, which is going to be RT1 by P1, right? This is what you are telling, right? V2 is going to be RT2 by P2, right? We know P2, T2, P1, T1. We just need to find dV or delta V, which is nothing but V2 minus V1, right? Yeah, this is also you can do. So why don't we do both? And of course, both will be same. The reason is these are mathematical functions, right? It should be same. So how does this work? What is this? It is going to be what is this one? This is going to be RT by P square, right? So it is 1 by P, so P square, and this one, sorry, minus RT by P square. So what happens here? Minus RT by P square dP plus dt by P, right? And we need to know what is R. So in the question, it didn't say anything whether it is R or not. So for now, let's consider it's an R, and let's solve 0.287 kilojoules per kg Kelvin, right? If you and what you need to do after this, you need to integrate it from 1 to 2. So it's going to be V1 to V2, and integrate this from P1 to P2, and integrate this from T1 to T2. So what happens now? So it's going to be R by P into T2 minus T1, and RT by P square dP. What is that? So we can take RT outside, minus 1 by P square. So it is P power minus 1 by minus 1. So minus into minus plus 1 by P, P1 to P2, right? Am I right, guys? Then let's say if you continue 0.287 into T2 minus T1 is going to be 5 Kelvin, 5 Kelvin divided by pressure. Now what pressure will you take?
So is this a new result anything? dB equal to, we have found out this specific volume change equation. This is actually an equation, isn't it? Uh, can we take it this as any result or anything?
Can you repeat, Francis? I didn't get.
Uh, can we use this equation as any as a result? Like, is this any another form of ideal case equation? Like, can we use this for any problems?
Right. So we will be using this in some places, right? So which equation you are telling?
This equation, I mean, we have found out dV, say dV equal to R by P, P2
Right.
minus.
Right. This equation So this equation, right? This is just mathematical derivation of V. So it is true for any simple compressible substance. We don't know whether it is ideal gas or not, right? So only when you have ideal gas you can substitute here. This equation can be useful when you have other gases. Let's say you have van der Waals equation of state. At that time you can easily use this kind of systems. I mean this kind of equation to find out the changes.
Okay, sir.
Okay. So have you guys solved the problem? Can you guys substitute it and let me know what is the answer?
So can you show those values?
Okay. Yeah.
So here for the value of PV, which one will be taking? I mean, R by P, we have two states of pressure is there.
Come again. R by P. We have two sets of pressure. Yeah. So what should we use?
Is it the initial one? The other term have is will be having two pressure since it's a limit in the limit
But
code.
still we have temperature also, right?
Yes, sir.
So one more thing. What we need to find is dV, right? Do we need to do this integration? So why do we require this integration? Is my question clear? So let's just put it here. dV is equal to minus RT by P square dP plus R dt by P, right? So we already know dP. How much is dP? The change in pressure from 100 kilopascal to 96 kilopascal is minus 4 kilopascals, right? And we also know dt. It is going to be 305 Kelvin minus 300 Kelvin, which is 5 Kelvin. The reason we couldn't do that is uh, we when you do the integration you cannot take P as a constant and you cannot take it outside, right? Let's say you can even do integration, still you can arrive at the same results, right? So let's say if you do like this, you are going from first state to the second state, right? From first state, what is the dP and what is the dt, right? And then substitute those things here, you will get the dV. This is one way. Or if you want, you can integrate it and also you can get it. Okay. So try integrating and let me know what happens. So let's say this is T by P square into dP plus dt by P minus 0. Let me write it here, minus 0.287 into 10 power 3 into temperature is 300 Kelvin, because we are going from first state to the next state, right? So for a small change in pressure you are trying to find, and the pressure is 100 kilopascals which is going to be 100 into 10 power 3 whole square times dp, which is going to be minus 4 plus dt, which is 5 divided by 100 kilopascal. So now my question is, why can't we do integration also? Why not integration? Is my question clear? So dv is again minus RT by. So quickly find out this answer. Let's see. Let's do integration and also check. The reason is these are subtle differences which we get confused often. Dt by p, right? We also know PV is equal to RT. So what if we integrate it? Integral of RT by P square dP from P1 to P2 plus integral of R dt by P from T1 to T2. This form is as usual, it's going to be simple. It's going to be R times T2 by P2 minus T1 by P1. So if you compare these two results, again you will be getting same. So, but why not we do integration also? That is my question. Think about it. So how much is the change in volume coming on? (300 into minus 4 divided by 100 divided by 10 power 6). Right?
So minus 0.0143.
So, and how about this? Meter cube per kg. So why there is a minus here? The change in volume, should it be positive or negative? We are moving, increasing temperature, right? Let's find out this one. How much is this one? So it's again 0.287 times T2 is going to be 300 divided by P2, which is 100 into 10 power 3, right? Sorry, it's T2 is 305 and this is 96 into 10 power 3. I think it's 96, is it? Yeah. And minus, what is T1? It's going to be 300 divided by 100 into 10 power 3. How much is this coming? These two things should match. It's a simple problem, but how much confusions does it make? See? So 96 divided by 10 power 3 minus 300 divided by.
So I'm getting 5.082 into 10 raised to minus 5.
Okay. So this is 0. Sorry, how much is it? 5.08.
0.08 into 10 raised to minus 5.
Okay, 10 power minus 5 kg per meter cube. So this is for sure is the right answer. Okay, that is right. But what happened here? So the only confusion is what is this T and P should be, right? What is this T? What is this P? I used 100 kilopascal and 300 Kelvin. Should I use that or should I use something different? And one more thing, sorry, I think there is a mistake in the algebra itself. So if you look at it, I took a minus outside, so there should be a minus here. There should be a minus here, right? So how much is this coming now? Let me look at it. 300 divided by 100 divided by 10 power 3. I confused even a simple sum, right? What happens? So I am not getting 0.0142. Francis, can you check again? I am getting something like around this value, 5.08. So it's going to be 300 into 4 kilopascal. That's 5 divided by 10 power 5. So this is at power 3. Kilopascal is 10 power 5, right? 10 power 5. All right. I think you guys are more confused. I'm going to leave it like this. So what we should do is, I will tell you. See, I should get the same result as this. This is the right answer. But what is the problem with this approach is what I'm trying to convey. So the reason is you found this correctly, but only thing is what P and T is the problem. So this is the problem. What P and T should I use? So in the process, I am changing pressure from this to this. So ideally, you shouldn't take the P1, you shouldn't take P2. Instead, you should take some P average. So since you take P average, this dV becomes an approximate. So you would expect value something close to this, but you will not expect exactly this. Okay. So let's say P average is 100 kilopascal plus 96 kilopascal divided by 2, which is 98 kilopascal. Right. Similarly, T average. What is T average? T average is going to be 300 plus 305 divided by 2, which is going to be 302.5 Kelvin. And let's say if you substitute here now, uh, let's take minus sign inside for convenience, and now we find T average, which is going to be 302.5 divided by 98 kilopascals 10 power 3 whole square into minus 4 kilopascal 10 power so if you take minus inside, there should be a minus here, 10 power 3 minus change in temperature, which is going to be 302 point sorry, which is going to be 5 Kelvin. It is going to be plus here now because we take minus sign inside, and now we have pressure here, which is 98 kilopascal, which is 10 power 3. Right. Now can you find the answer and let me know what is the right answer? Everything is positive here if you note. What is the answer you get? Let me also calculate. 502.5 into 4 into 10 power 3 divided by 98 square plus 5 divided by 98. I think it's 0.5 10 power 3 divided by 98 plus 5 divided by 98 into 10 power 287. Something like 0.0508 meter cube per kg. There is a 10 power minus 5 here. Is the calculation here right? 305 divided
Sir,
by
I'm getting zero same value.
okay, this value is right.
Yes, sir.
Okay, how about this value? Is this value right?
So I think in the below equation we didn't have used we have used point two itself. I think using the 10 cube could, I mean, 0.287 into actually I
Okay,
think
okay, okay. So you forgot to multiply 10 power 3, right? So
yes, sir.
basically it will be 10 power minus 2. So if you calculate more accurately, can you? So here I'm getting around. Uh, let's calculate for a few more decimals. I want to show you the difference between these two. So 5.08 01 01701. Okay, and if you calculate here, how much is it coming? Can you calculate it for, let's say, 4 decimals divided by 96 into 10 power 3 300 divided by 100 into 10 power 3. So I am getting something like 5.0823 meter cube per kg. Okay. So if you look at it, there is a difference between these two. The reason is we did this approximation. So this is a continuous function, so you need to do a integration. Okay. So now if you follow this approach, let's say you do the integration. Here p has to be substituted because p is a function of v, r and t, right? So you need to write p r t by v to b, sorry, p to b r t by v. Then you need to substitute it here, and then if you perform this integral, since it's a smooth function, pv is equal to rt is a function, since it's a smooth function, you will be able to get this results. So please try this at uh, uh, you have free time. Okay. So that is the important thing I want to show you. Even though it's a simple problem, it teaches us a lot about the differentials. How do we use it? Okay. So let's say if you go for a very complex function, complex real gas equation, let's say for some substances there is no equation, there is only tables, right? So they don't have any functions. PV is equal to RT is not there. So when you have such kind of gases, when you deal with such kind of gases, you may need to do this integrations. So you may need to do this kind of uh, approximations to find an approximate TV. That is the reason. That is one of the reason why we need to follow this. Why we need to know this kind of approach to find a change in volume. If it's a simple ideal gas, this is the most accurate method. Since you know the relation, you can easily find it. Okay. So that is what I want to emphasize in this problem. And is there any doubts? So what did we do in here? The main thing is this approximation, which you need to um, remember when you do such kind of problems. If you are just want to solve this equation, let's say in gate, it's just better to go with this. This is just for your understanding. Okay, right? If there are no more questions, let's jump into one interesting question here. I have uh, a chair which is on ice rink. Okay, so there is some ice cube or something, and above that there is a four-legged chair. Okay, consider a four-legged chair rest on an ice rink. The total mass of the chair and the person sitting on it is 85 kg. So there is a person sitting on the chair and the total mass is going to be 85 kg. If the ice temperature is minus 2 degrees Celsius, determine the minimum total area the tips of chair legs can have before the ice in contact with the legs would melt. Okay, so please understand this line, and let the local acceleration of gravity be 9.8 meter per second square. So what they are telling is there is a ice cube or ice slab. Above that there is a chair and the person is sitting on the chair. So now we know that there is the ice starts melting, right? So there is because ice melts at certain saturation temperature and pressure. Now since we are sitting on the chair, the pressure exerted by the chair on the ice would be different compared to the other places where the chair is not present. So in those places the pressure would be more. Because of that, there is a possibility that ice could melt or the temperature could vary, right, because of pressure. So they were asking what would be the minimum area of that chair should be such that this ice won't melt, which means what it tells. So basically it is telling that the pressure exerted by the chair should be less than the saturation pressure of the ice at that temperature. So because of chair present, there is a temperature change of minus 2 degrees Celsius. Initially it would be 0 degrees Celsius, right? And because of pressure exerted, there is a temperature change to minus 2 degrees Celsius. and because of that the saturation pressure would change. And if you there is a possibility the pressure would be greater than the saturation pressure, and there is a possibility that it would start melting. So we do not need that. And that is the reason we need to find what is the minimum total area, so that we can distribute that pressure, and we can make sure that the pressure is below the certain saturation pressure. So if we start solving it, it will be more clear. So is the um, question clear for everyone? So this is the ice, right? There is a chair over here. This is a chair, and there is this places where the ice is exposed to chair, right? And there is a force acting downward, which has 85 kgs, and acceleration due to gravity. Some force is acting on the chair, which is going to create pressure over here, right? Now we need to find what is this area. Okay, so let me write it down. uh, what is the area of the chair, especially the legs are in contact of ice. So what is this? So what they are asking. So for that we need certain saturation pressure and temperature data. So what I would do is at 0 degrees Celsius, let me give, so usually it is going to be HIF, which is uh, enthalpy for phase change, right? Enthalpy of melting here. Okay, that is around 334 point, sorry, 333.4 Kelvin, 4 kilojoules per kg. Okay, and the specific volume of ice at that state is going to be 1.0911 into 10 power minus 3 meter cube per kg, and Vf is going to be 1.0002 into 10 power minus 3 meter cube per kg. Okay, now uh, we also know the P saturation at 0 degree Celsius, which is 0.61 kilopascal. So these are the data is given. Okay, now we know that ice temperature of ice, right, which is nothing but minus 2 degrees Celsius, which is around 271.15 Kelvin, right? So this is 273.15 Kelvin or 273 Kelvin, whichever is convenient for you. So here they have given the temperature of ice is minus 2 degrees Celsius. So how do we find the minimum total area? Is the given data and the question clear? So why do we even need to find minimum total area? So that should be clear, right? So is everyone able to follow?
Yes, sir.
Okay. So so there is some so let's look at this more carefully. So there is some guy sitting on that chair, and he is going to exert some pressure on that ice. Okay. So let's say that pressure is P2 or something, or P, what do you call, P char, let's say. Okay. So this is the pressure exerted on the ice on that small area. Okay. Now, um, let's draw phase diagram. Okay, here we have P and here we have temperature, and we know for an ice it's going to be, this is the fusion curve, right? This is the fusion curve. Other curves we are not interested, because we are interested in going from solid to liquid, right? So now, so this is going to be liquid, right? This is going to be liquid and this is going to be solid, right? Now what I'm trying to do is, I have at 0 degrees Celsius, this is the P and T I gave. So this is P saturation, this is T saturation. Okay. Now what I'm telling is my ice is at minus 2 degrees Celsius, which is little bit less, right? Let's say somewhere over here. Okay. Now I am trying to find out what is this P. So this is P. Let's write P naught and P1. Okay, this is, let's say, P1 and this is P naught. This is P naught and this is P1. And I know that this is T1, which is minus 2 degrees Celsius, and this is 0 degrees Celsius, which is T naught. Okay. Now, how do I find this P1? So basically, if I find P1, we know that the force exerted by the uh, okay, let's try to answer that also. Let's say if I find P2, somehow I found the, sorry, P1. Okay, the pressure exerted by the chair. Okay, that is going to be nothing but pressure of the atmosphere, right? P atmosphere plus the force exerted, force by area, right? Pressure is nothing but force by area, force exerted by the chair, which is nothing but P atmosphere plus the force exerted by the chair is going to be mg by a. Okay, P atmosphere we already know it's going to be uh, bar, right? So mg by a, m is given, g is given, so we need to find a. So for everything we need to find, so to find a, we need to find P1. Based on this given data, how can we find P1? Because we know the temperature is going to be minus 2 degrees Celsius, we can find P1. So how do we find P1? Okay, you guys are thinking too much. We already talked about this in the lecture, right? So it's going to be Clapeyron equation. We can use Clapeyron equation. Okay. So what is Clapeyron equation? We know we actually need to find saturation. These are saturation pressures, right? We need to find saturation pressure, because that is the pressure in which ice will remain as ice. If not, it would be or the if the pressure should be less than or equal to saturation pressure. If it is more, it's going to become liquid, which we don't need that, right? So the minimum area can be obtained when we have a saturation pressure. So that we will see, with that point we will come back again. So basically, we need to find saturation pressure, and what Clausius, sorry, not Clausius, the Clapeyron equation says about saturation pressure. It's going to be dP by dt at saturation is going to be HF minus HI, right? If you would have studied like Hg minus Hf, because that is for liquid vapor conversion. Here it is solid liquid phase change. Okay, and times T times Vf minus Vi, right? So this is what Clapeyron equation is. Now we if we assume the enthalpy change due to phase change, and the volume change is almost same. Okay, if we assume HIF and VIF is same or is almost same when the temperature changes, it's almost same, 0 degree Celsius and minus 2 degree Celsius. Let's say if we assume that, this is one assumption. If we assume that, then we can use this given data over here. Okay, so how do we do that? We have dp by dt, and then HIF is already given, 333.4, 333.4 into 10 power 3 divided by uh, temperature. Here it is going to be minus 2 because ice is at minus 2. We are not going from 0 to 2. Okay, so if it is minus 2, it's going to be 271.15 Kelvin times Vf minus Vi, 1.002 into 10 power minus 3, 1.002 into 10 power minus 3 minus 1.0911 into 10 power minus 3, 1.0911 into 10 power minus 3. Right, so how much is dp by dt coming now? Or instead, let's do this way. Let's not calculate now. Let's continue it. So ultimately we need to find pressure. So if we find dp by dt, it will be of no use. We need to find pressure, right? So let's say dp is equal to HIF by VIF into dt by t, right? And we are interested in finding the pressure from uh, P0 to P1 and T0 to T1, right? So it's going to be P1 minus P0 is equal to HIF. If we assume these two are constant, it's not a function of temperature, okay, or almost same for 0 and minus 2 degrees Celsius, then this becomes ln of T into T0 and T1. So this we can rewrite it as HIF VIF ln of T1 by T0, right? So P1 can be written as P naught plus HIF by VIF ln of T1 by T0. So basically dp by dt we no need to find, it's of no use for us. After that anyway we need to find pressure, right? That is what is important. So if we continue substituting it, we'll end up expression like this. So now P naught, what is P naught here? uh, we are going from, we already found, it's already given, right? So it's 6.61 kilopascal, which we can write it as 0.61 into 10 power 3 plus 333.4 divided by 1.00009 or what is it? 02 into 10 power minus 3, and ln of T1 is sorry 271.15 divided by 273.15. Okay, and what is this pressure? Let's quickly find out. It's going to be 271.15 divided by 273.15 ln of 333.4 divided by 1.0002 minus divided by 10 power minus 3, right? Plus 0.61 into 10 power 3. Which are you guys getting?
Sir, I'm getting 28108.
281.65.
08.65.
So it is in pascals, is it? Okay. So slightly different answer. Let me check again. 271.1. Three plus 0.61 into 10 power 3. Okay, I'm getting 276. Anyway, it's fine. Let's see what happens. So now we have this much pascals, right? So that is going to be equal to PATM plus mg by A. Sorry, capital A. And so this pressure is, I think there is something problem with the solution. Did we add kilojoules properly? Huh, super. I think we missed another kilojoules here, 10 power 3. So how much is it coming now? You should be very careful with the 3, 4, 10 power 3 by 1.002 minus 1.0911 divided by 10 power minus 3 into ln of 271.15 divided by 273.15. Yeah, plus 0.61 into 10. Francis, how much are you getting? E1? So please note that it is in kilojoules, right? So we need to multiply by 10 power 3. 269 point, let's say 55 bar. Is that what you are getting? So it's around into 10 power 5 pascals. So we already told that P is nothing but PATM, right? Plus mg by A. Okay. Let's say if we rearrange this, um, we can rewrite it this as A is going to be mg divided by P1 minus P80. So this is going to be 85 kg into 9.81 divided by P1 is going to be 269.55, this much power minus 1 into 10 power 5. How much is the area coming around? 269.55 minus 1. 80. I'm getting around something around 322 into 10 power minus 7. I'm not sure whether it is, whether you are also getting the same results. Is that clear, everyone?
So can you summarize it?
This is how, so this area is fine, right? So what I'm trying to say is this is the least, this is the um, minimum area. You can have a bigger area than this, and you can have uh, it is safe to have a bigger area than this if you are, you know, if you are uh, having a, if you are exerting only 85 kgs of force, right? So the reason is when you have this much area, the pressure it exerts on the ice is going to be P1, which is a saturation pressure. But if there is any possibility, if the 85 kg increases, right, then P1 increases. If P1 increases, what happens? This for this temperature, it will be in the liquid side, right? So P1 increases. So for any small change, it will be in the liquid side. If it is in the liquid side, then everything will start melting. Ice will start melting. It is not safe to sit above ice anymore, right? So these things we use in, let's say, if you are going in Antarctica, if you are building a um, tent or something, we need to know what would be the temperature range, what would be the temperature difference it would make, and is it safe to, what is the saturation pressure and how much pressure I can give. So that we need to know. So that is the reason we are doing this exercise. So basically what I'm trying to say is I can exert pressure only till saturation or less than saturation. And at saturation I will be having a minimum area. Okay. The reason is because it is inversely proportional. P is inversely proportional to area. So I can have uh, pressures less than P1 to have a to be in the safer side. Okay. If you cross the pressure, or let's say if you have lesser area, then P1 will be increasing. If P1 increases, then your ice starts melting. So that's why they ask what is the minimum total area you require. Okay. If you, the pressure would increase and it starts melting. That is what it means. Does it make sense?
Sir, actually, we use the Clapeyron's equation in order to find P1. The P saturated will be given.
Correct. So right. So this P1 is also P saturated only, but for temperature 2, right? 2 degrees Celsius. P1 is also P saturated, but it is for minus 2 degrees Celsius. So at 0 degrees Celsius, it's 0.61 is what the saturated pressure is. This is saturated pressure at minus 2 degrees Celsius. Is that clear? So with the given data, we are trying to find out what would be the saturation pressure at the minus 2 degrees Celsius, because we require saturated pressure in order to find what is the maximum safe allowable pressure it can be exerted on the ice. Is that what you're asking, Francis?
Yes, actually we are having the P saturated at the 0 degree Celsius, and
Hmm.
at the present condition the temperature is -2 degree. So at that -2 degree Celsius, we found out that what will be the pressure using Clapeyron's equation.
Correct, correct. Using this clashes Clapeyron. Sorry, just Clapeyron equation. You are right.
So that pressure should be using the then we equate the pressure with the mg value and the atmospheric pressure and find out the minimum area.
So that is the maximum pressure you can apply. So this 269.55 bar is the maximum pressure you can apply. So if that is the maximum pressure you can apply, what would be the area? You are just finding it.
So is there any specific reason that we use this Clapeyron's equation?
Right. You actually the reason to use is to approximate it and get what would be the saturation pressure in the surroundings, right? So we know only the that is the reason we use this Clapeyron equation along the fusion curve. So we do it only along the fusion curve. Along the fusion curve, how does the saturation pressure and temperature vary? We have a relation for it. So that is the use for this. Basically what we do is we can do by experiments, we can find this P saturation and T saturation for different pressures, but this equation gives us more easier way to find it.
So this Clapeyron's equation will be used by using this as a fusion curve, and also we have during the isenthalpic process we will be using this Clapeyron's equations again.
Yeah,
I mean throttling.
yeah, we use. So there will be something you will study that in upcoming classes in throttling, what you will do. Okay. Basically, enthalpy is constant in the throttling process, and we use it has to something to do with chemical potential. So it will be in the coming week lectures. Okay.
So we'll be using this during the phase change process. I
Yeah,
mean,
yeah. Only during phase change processes we do Clapeyron
yes.
equation and Clausius-Clapeyron equation. It is to
Okay.
find saturation, pressure, and temperature. Okay.
Okay, sir.
All right. So if there are no more questions, let me go on with the third question. So the third question here involves a derivation, basically. Basically, you know that for a adiabatic process, we say PV power gamma equal to constant, right? Here K is gamma, so PV power K is equal to constant. Okay, that is what we used to write, but we took that for granted, right? So how can a isentropic process or an adiabatic process can have PV power gamma equal to constant? Is that what we are going to derive it? So let's say here consider a infinitesimal reversible adiabatic compression or expansion process. Okay, reversible adiabatic compression or expansion process. By taking S equal to P and V and using the Maxwell relation, show that PV power gamma is equal to constant, where K is isentropic expansion exponent defined as this. Okay, this is how gamma is defined basically, but we used to write Cp by Cv, right? That is true for ideal gas. If not, this is the general formula. So that isentropic exponent K reduces to specific heat Cp by Cv for an ideal gas. So we were asked to uh, show that the process is really a PV power gamma equal to constant. So how do we do that? Since we know that it's a reversible adiabatic process, it's going to be an isentropic process. Okay, and they also gave a hint to start from S as a function of P and V, reversible adiabatic process. Okay. So then yes we are taking S is a function of P and V, and for a reversible adiabatic process the entropy change is going to be constant, right? Our entropy change is zero, entropy is going to remain constant. because it's an isentropic process. So if that is the case, that the change in entropy is zero, which means ds equal to zero. And if ts is equal to zero, we know s depends on p and v, right? So maybe we can expand this. So how can we write it? We can write dou s by dou p at constant v dp, and we can write dou s by dou v at constant p dv, right? And we know that ds equal to 0, so this is equal to 0. Okay, this is clear, right? Now if this is clear, let me just write it down separately. Dou s by dou p at constant v dp plus dou s by dou v at constant p dv is equal to 0. Okay, now we can use Maxwell relations. So can you guys guess what kind of what relations we can use here? So basically we need to come up with PV for
Previous
gamma
equation.
equal to TDS equation. Go on. What which equations you will use? So let's say for dou S by dou P at constant V, what this is equal to and what this is equal to. Dou V at constant V. So that Maxwell relation is actually uh, has a relation from the, let's say, U, H and S to, sorry, U, H and Xi, right? Internal energy, enthalpy, and uh, Gibbs free energy and Helmholtz free energy. It will relate it to the properties of the system like P, V, T, and S, right? So here also we have S, all these properties. So we can relate it in terms of independent properties also. So what is the relation? Francis, go ahead.
I have a question that why these TDS equation cannot be used in the chemical reaction process. I mean, I found a statement that this TDS equation can only be used if there is uh, it can be used when there is a chemical reaction.
Which TDS equation? There
I
are
mean
two
the
TDS equation, right?
uh, I
Q is equal to
according to
TDS minus PdV. This is one relation. DH is equal to TDS plus VDP. I think this is right. Uh, it is was the problem in chemical reactions. We can't use it. Is that what you're telling?
yes, one of the statement it was like TDS equations are used when it is in the when it cannot be used when there is a chemical reaction like
So the TDS equation has one assumption. This is for pure substance. When there is a chemical reaction, we have different substances, right? Different mixtures. It's a mixture. There is a reactant A, reactant B will give you product C and product D, right? So it's a gaseous mixture. So the TDS uh, equation will be transformed, which also includes those mass fractions and mole fractions. So this is for simple substance. Okay, this is a simple pure substances. For pure substances, you can use it. For reactions, there will be additional terms. That's it. So those things you will learn when the combustion module comes in. Okay.
okay TDS equation can be only used with the pure substance with the constant composition.
No, there is no such thing called constant combustion. This is only for pure substance. Pure substance going through a phase change. Pure substance going, or pure substance in a compression or expansion process. So let's say if you go into combustion, let's say hydrogen and oxygen, it reacts and gives you H2, right? So when you do that, there will be additional equations, additional terms in this TDS equation. So this is for pure substance. It is not for mixtures, gaseous mixtures. That is what I think. That's why it cannot be directly employed to chemical reactions. But there will be additional terms coming in addition to this TDS equation. There will be some additional terms which involves mole fractions and mass fractions. Okay, and when you add that, then that would be the TDS equation for the gaseous mixture. So that part you will learn it soon. Okay.
Okay, sir. And also this TDS equation cannot be used in the irreversible process. Can it be used in the irreversible process?
Uh, so this part you need to be a little clear. See, if you look at it, this is from first law, right? So this
Yes,
is
sir.
an important point actually. So du is equal to del q minus del w. This is the first law, right? This is true for either it is reversible or irreversible. But then what we do is with the help of entropy concept, and since it's a simple compressible substance, we can replace dw with pdv, right? So this we can replace it as tds minus pdv, right? So but when you do that, you might tell that it is only for reversible process, but it is not. It is true for both irreversible process also, because what you are finding is you are finding entropy, and entropy is a change in entropy is a property of a system. It doesn't depend on the path, but del q depends on the path. This is path dependent, right? Whether it is a reversible or irreversible, it needs it needs to know, the del q needs to know. But tds it no need to know, it is path independent. If you look at it, t, s, p and v all are state functions, not path functions. So this is actually true for both reversible and irreversible process.
Okay, sir.
So is that clear? That is, this is a subtle thing. The reason is del q we, because ds is equal to del q by t only for a reversible process, right? So that is the reason you will be thinking that it is only for reversible process. But then uh, what do you say, the form it takes is contains only properties, like contains only state functions. So t, s, p and v are state functions. It doesn't depend on path with which it follows. So it can be reversible, it can be irreversible, doesn't matter. So this is you true for both reversible process.
Okay, sir.
Okay? This is actually an important thing. People usually used to miss it. So TDS relation is true for both reversible and irreversible. In fact, we use TDS relation for chemical reaction, and chemical reactions are, there is no kind of reversible combustion. Combustion is purely irreversible, right? So so what are the TDS relation for this? Coming back to our question, what is the Maxwell relation for this dou s by dou p at constant v and dou s by dou v at constant p? I know remembering all the relation will be quite intimidating, but there is no other way. We have to remember it. So dou s by dou p at constant v is nothing but dou v by dou t at constant s. Okay, and dou s by dou v at constant p will be dou p by dou t at constant s. Okay, let's say if we substitute it here, what happens? Minus dou v by dou t at constant s tp plus uh, dou p by dou t at constant s pv is equal to 0. See, these are at constant entropy only, so we can actually drop this uh, part. Anyway, so let's say we will rearrange this.
So I have a doubt that why we actually, is there an application for this acceleration? Actually, we we are actually writing these partial differential form. Writing these equations. Uh, does these equation have any physical applications, like, uh, or just it's for the sake of the derivation or anything?
So, so till now, so without doing this Maxwell relation, how do we know PV power gamma equal to constant for an irreversible reversible adiabatic process?
So PV gamma is derived from these equations.
Right. So this is derived from these equations, but usually we take it for granted and we'll just use it PV power gamma equal to constant. But if you continue this process, you will end up seeing that. And one more thing is these relations would be helpful when you have, since it relates internal energy, enthalpy, and entropy to pressure, temperature, and volume. So let's say if you have pressure, temperature, and volume, you can easily map it back to a change in internal energy, change in enthalpy, and change in entropy. So basically, the next problem is going to be related to that. So you can let's say if you have here the change in enthalpy of the air, you need to find out for a different equation of state. It is no more a ideal gas equation of state, but it is a some other equation of state they give. So the gas is as some other equation of state. So if that is the case, if you want to find the change in enthalpy, you may need to go and check in the tables, and then you can find it. Or uh, or for all the gases, for all the real gases, you will not have tables, and you will be given some equation of state. So for that, when you want to find out, these relations would be helpful. Okay.
Okay, sir.
Right. So let's continue and finish it. So let's try to rewrite this. Let's say if we rearrange uh, based on pressure. Okay. So we can write dp minus dou t by dou v at constant s times dou p by dou t at constant s dv. Right. Basically, I divided by minus of dou v by dou t at constant s. I'm just trying to get the p and t separately. Sorry, p and v separately, because pv power gamma is equal to constant. Okay. Now, since these two are entropy, constant entropy, we can write it like dou t by dou v times dou p by dou t. All these are at constant entropy. Anyway, the process is also constant entropy, and so these two we can cancel it out. So this becomes dou p by dou v at constant entropy dv is equal to 0, right? And what can we do after this? So we it's already given that k is nothing but, let's use this information, k is nothing but v by p dou p by dou v at constant yes, right? So this is already given. uh, let's say let's substitute this here. Okay. Dou p by dou v constant yes is nothing but kp by v. So we can write dp minus k p by v dv is equal to 0, right? um, let's rearrange it. Dv is equal to my if you take this to other side, kp by v dv, and this can be written as dp by v is equal to k by v dv. Now if you integrate it, so ln of p becomes k times v, some constant. This also can be ln of c or something. So now how do we write it? So we can write it like v power gamma, right? Uh, did we write it right? dp by p. Oh, there's a k. Okay. So actually there is a minus here. I missed it. Okay. So if that is the case, we will have another minus here, and if that is the case, we will have plus here, and then we will have minus here. We will have minus here. So then here also we will have minus. Okay. Now we can take k to the power of v. You can write ln of v power minus k plus ln of c. This is just a convenience, right? So ln of p can be written as ln of c times v power minus gamma, where c is just a constant. So we can write p is equal to cv power minus gamma, then pv power gamma is equal to c. So this gave us an uh, I mean, this TDS, like the Maxwell relations, helped us prove that V power gamma is equal to constant, right? So, is that clear? So, what did we do? So, we just applied two Maxwell relations, we just substituted it, and then we simplified it. That's it. These two are Maxwell relations. Now, the second question here asked is if show that isentropic exponent K reduces to specific heat ratio Cp by Cv for ideal gas. So they are telling show K is equal to Cp by Cv. So we know that K is nothing but minus of what did I write here? V by P, V by P, dou P by dou V at constant entropy. Now we need to prove that this is equal to Cp by Cv. How do we prove it? So I will discuss here the method. How can we do it? Uh, so basically, if you remember, the everything here is entropy is constant. So we can use that information. In fact, gamma is always Cp by Cv. So actually, it is general. It's not for only for isentropy. Here, S is nothing but S is a function of P and T. S is a function of S can be a function of P and V. S can be a function of P and T. S can be a function of V and T. Right. So this is also true. Now, what we can do is we can have this cyclic relation equation, like the cyclic relations, where we say that dou P by dou T at constant S times dou T by dou S, dou T by dou P by, so yes, T and P, right? So dou T by dou S at constant P, and dou P, so dou S by S P and T. So P T S T S P S P T. This is going to be equal to minus 1, right? This is a cyclic relation we used. Similarly, we can write this as dou V by dou T at constant S, and dou T by dou S at constant V, and dou S by dou V at constant T is equal to minus 1. Now we know that we know that we know what is Cp, right? So let's say if you write we know for this we know that ds is equal to Cp dt by T, and I think minus r dp by p, if I remember correctly, right? So cp dt and minus r dp by p. So then this relation you can also write it like dou s by dou p at constant t dt plus dou s by dou t at constant p dp. You can write it like this, right? So if that is the case, then cp is equal to this, where we can write cp is equal to t times dou s by dou t at constant p. Okay. So there is this relation. Similarly, we have cv relation. Okay, and then you substitute these two relations here. Okay, and let me just give you an outline. Once you do this, it will be a function of cp, and this will also be a function of cv. Then take the division of these two, cp by cv, which will be something like this. Okay, let me just give you that also. So we finally write cp by t is dou p by dou s at constant t, and dou t by dou p at constant s is equal to minus 1. Similarly, cv by t times dou v by dou s at constant t and dou t by dou v at constant s is equal to minus 1. Now you took division of these two, cp by cv. So once you do that, you will end up getting something like this. Okay, so here when you do division, you can put it up in the numerator just by inverting this numerator and denominator, right? So cp by cv, how you can do dou p by dou s at constant t and dou t by dou p at constant s, right? And you can actually put it in the multiplication, dou s by dou v at constant t and dou v by dou t at constant s. Then if you take the let's say take temperature constant and entropy constant, what happens is dou p by dou v at constant temperature you will get. Similarly, here also temperature and temperature you can cancel it out. Here entropy you can cancel it out. Then you will end up getting dou v by dou p at constant yes. Okay, this is cp by cv, is that what you will get, dou v by dou p. Am I right? Temperature. Okay, now once you do this, so this you can replace it as so you will be getting so you need to find dv by dp, which is going to be, we already know it's ideal gas, so it's going to be p rt by p divided by dou p, right? And then at constant temperature, let's say this can be written as, since dou p by dou p gets cancelled, and it becomes minus v by p. And now if you rewrite this as cp by cv minus v by p dou p by dou v at constant yes, this is what it becomes, and this is nothing but gamma. Okay, a little bit here, but you please complete this proof. Okay, if you follow this path again, you can complete this proof and let me know whether you are able to get this. There might be some algebraic mistake here. Okay. So, so this is at temperature. This should be, this might be at entropy, and this might be temperature. Check this. Okay. So finally you will end up getting this. So only thing is you need to find Cp by Cv. That's it. So you need to find Cp and you need to find Cv using this relation. So once you find this, if you just simplify it, you will end up getting this, and that is eventually will become gamma. Okay. So I hope this outline would be helpful for you to find it. Okay. We have last 10 minutes. Before that, we will try to finish this final question. Okay. Is there any questions in between? So till this, it would be clear. After that, I went a little faster, but you take your time to finish this. Okay. Coming to fourth question, we are asked to find the change in enthalpy of air. We already discussed before. As it undergoes a change of state from this to this, and 800 kilopascal to 420 degrees Celsius. Okay. So let me write it out. So it's there is a T1 and P1. This is the state one. Okay. T1 is 34 degrees Celsius and P1 is 100 kilopascal. It's a change and it becomes T2 and P2. So T2 is 420 degrees Celsius and P2 is how much? 800 kilopascal. And this gas is not an ideal gas equation. Ideal gas here. So the equations of state changes. The equation of states becomes something like P times P minus A equal to RT. Okay, where A is also given. A is nothing but 0.01 meter cube per kg. Okay, this is the equation of state for this gas. Now you are asked to find the change in enthalpy. Okay, and then compare the result to the value obtained by using ideal gas. So you are asked to find change in enthalpy for both uh, uh, ideal gas ideal gas and the real gas, which has equation of state PV P times P minus A equal to RT. Okay. Now we need to find change in enthalpy, which is dH. Right? How do we find dH? So we know H is a function of temperature and pressure. That is clear, right? So it is just function of temperature and pressure. Internal energy is a function of temperature and specific volume. Enthalpy is a function of temperature and pressure. So the same thing we need to do the total differential, which is nothing but partial derivative of dou H by dou T at constant P dP, right? Sorry, not dP, it is dt. So here the derivative is d to dt, so the same derivative should be there, plus dou H by dou P at constant T dP. Okay, and what we know is, we know this is Cp, right? We know, so that is the definition of CPUs. And usually for ideal gas, this the enthalpy is for constant pressure. We actually do not have this term, so we will see that for ideal gas. For this we will try to find out, since dH is nothing but now Cp times dt plus dou H by dou P at constant T dP. So here it is for constant pressure. Another thing is, here it is for constant pressure. For in a constant pressure process, the change in enthalpy for a change in temperature is nothing but specific heat. That is the definition of specific heat. So that's why we wrote it like this. Okay. I hope that's clear. Now, how do we find dou H by dou P at constant T? We can find it through TDS relations. Okay. So we have dH equal to TDS minus VDP, sorry, plus VDP, minus is for internal energy. And we know about ds, we know about ds is nothing but dou S by dou T. S is also a function of temperature and pressure. Dou S by dou T at constant p dt plus dou s by dou p at constant t dp. So let's substitute it here. dh is nothing but t times dou s by dou t at constant p dt plus dou s by dou p at constant t dp, and then we have additionally v dp tau. Okay, now let's combine these p's together, dt and dp together. um, let's say if we do that, so t times dou s by dou t at constant p dt. Again, we know that this part is cp, right? Okay, we'll come back to that later. So this part is going to be cp already, right? Let's we'll come back to that again. And we have dp, we take dp to be we will take dp as a common here. T times dou s by dou p at constant t plus v times dp, right? So I just found two relations here. One is from tds relation, one is from uh, the definition of exact differential, right? The definition of, so if we compare these two, if you compare these two, it is clear that cp is going to be this, and dh by dp at constant t is going to be this. So let's use this knowledge. Okay, dou h by dou p at constant t is nothing but v plus t times dou s by dou p at constant t. Okay, now uh, we know about dou s by dou p at constant t. There is one Maxwell relation, right? Maxwell relation for dou s by dou p at constant t, we already, I think we did here. Dou s by dou t at constant p. Can you guys quickly tell me what is the Maxwell relation for that? So have a look if possible. Dou s by dou t at constant p. Dou v by dou t at t constant p, right? Dou v by dou t at constant p. Nothing but dou v by dou p. So dou v by dou t at constant p. This is one of the Maxwell relation. So we were able to convert this. Now since it is in terms of v, t and p, we know the ideal gas equation of state. So let's find dou v, sorry, we know the equation of state. Dou v by dou t at constant pressure is going to be, uh, rewrite this. P minus A is nothing but RT by P. V is nothing but A plus RT by P. Okay, so now this is for a constant pressure process, and if we do that, it's going to be R by P. Let's substitute it back. So dou H by dou P at constant T is nothing but V plus RT by P. Okay, so RT by P is nothing but V minus A, right? V minus A. So this is going to be V minus, I think there is a minus missing here again. Maybe this is minus. I think. Let me check. Yeah, see here we have minus here. Sorry, this is minus. So uh, This is going to be minus of V minus A, which is going to be A. So in a way, we have enthalpy as a function of both temperature and pressure. If you look at it now, dH is nothing but Cp dt plus dou H by dou P at T is nothing but AdP. So this is the enthalpy function for the equation of state PV minus A equal to RT. Okay, so but if it is an ideal gas equation of state, we do not have this. We have PV equal to RT, right? So basically A is 0 for an ideal gas. So this part goes away. So for an ideal gas, H is a function of temperature only. It is not a function of pressure. Okay, but this gas has some dependence with pressure also. Now we know this. It should be straightforward. We have P and T's. We'll substitute it here. We need to know Cp. Cp is not given, right? Okay. Cp is not given. You can take a Cp value. Let's say 1.007 kilojoules per kg. Usually it will be given. For this questions, it's not given. Okay. Now you can find the change in enthalpy, which is nothing but 1.007 into 10 power 3 times the temperature difference plus 0.0001, I guess, times pressure difference. So pressure difference is 420 minus 34, 800 minus 100, 420. So now you are able to actually find what is the change in enthalpy just by knowing P and T's. So we explicitly derived dH equal to Cp dt AdP, so which is not readily available for any other gas except ideal gas. Ideal gas is dH equal to Cp dt. So this is the dH for this gas. So how much are you guys getting? So for an ideal gas, it's simple, straightforward. Uh, Ideal gas is nothing but PV is equal to RT, which you can actually write P into V minus 0 equal to RT, and you can say that is equal to 0, right? You can write P minus VA is equal to RT, and you can say A is equal to 0. So this AdP will actually become 0. So for an ideal gas, it is true that dH equal to Cp dt. So which you can write it as 0.07 into, again, 10 power 3. Please be careful. And 420 minus 34. This is your TH. So how much are you guys getting? Something around 388.7 kilojoules per kg, right? And this is around 0.01 into 700 cube per kg. 700 into 10 power 3, again 0.01 into 10 power 3 plus 388, getting something like 395.7 kilojoules per kg. So this is the difference between when there is a enthalpy change if it is an ideal gas and if it is a some other gas with some other equation of state. So you can use we use this TDS relation. Sorry, we use this Maxwell relation to do this easily. If not, you need to measure entropy and pressure. Like it is going to be very difficult, right? So in a way, this would be easier way. The Maxwell relations would be easier way to convert these things forth and back and forth. Is that clear? The last question.
Yes, sir.
I think there is no problem in the last question, but I think the third question has some problem because I missed some. I missed some. I made some arithmetic mistake here. The calculation mistake. You can go forward. This is the outline. You just need to use this. Find CP by. So CP is going to be something like this, I guess. See. The mistake is clear here. So this is going to be dp and this is going to be dt. So actually CP is this, right? Similarly, you can do CV, right? And once you do that, you substitute it here, and then you should be able to get results. So there's a T also missing. Yeah, you should do it little carefully. Okay, check this also. And then if you do this, you will be able to prove this also. I hope the other questions are also fine. Right, this is also one exercise you should do. Let me know what you are getting.
So actually, I have some doubts. Can I ask them?
Yeah, let's ask whether they have some other questions. Maybe.
Okay, sir.
If there are, we have Krishna Kumar and Sarita here. So, do you have any doubts? If you have any doubts, you can ask me. I'll be here. If not, we can move forward and we can meet next week.